So can you see the screen?
Yes.
Yes.
I think we stopped somewhere. We're still working with normal. We stopped here, I think.
Yes.
So we shall do some more. I think I'd asked you to do this. Or did I ask you to solve this one? You had the example here.
No.
Yes, but anyway, you can note it down and try to solve this one. This will be your exercise. So you need to, you've been given the group Z12, and you have a subgroup, 048 as a subgroup of Z12. And this is a cyclic subgroup generated by 4. Also 8 is a generator. Both 4 and 8 are generators. So the question here is, you need to determine all the left cosets of P in Z12. We did an example last time using a different subgroup. Use this 0369. So the advantage you have here is that Z12 is an abelian group, and any of its subgroups will be normal, and therefore you can always the factor group. You can construct this factor group, which consists of all left cosets of P, this subgroup P in Z12. So this is some work for you. Just go ahead and complete it. You can hear me?
Yes.
Okay, that's good. So we define some new concepts, new for us, but not entirely new in group theory. So we're going to define the normalizer of a non-empty subset. Let's see, someone is trying to join. Can admit them. So we'll define the normalizer of a subset of a group as follows. It says if G is a group and S is a non-empty subset of G, so we define the normalizer of S, which is denoted by this, the capital N with the S in the brackets. It's all elements in G such that XS, X inverse will be equal to S. So there are two ways you can write this. You can also write it as all X in G such that XS is equal to SX. Now here we don't care whether S is a subgroup. If it's a subgroup, there are some advantages we would have. But for now, we don't care if it's a subgroup or not a subgroup. We just need a non-empty subset of G. So this set is called the normalizer of S in G. Now, if S contains only one element, if S is just made up of a singleton, then we write the normalizer of that set as n of X. That is if X is the element contained in S. It's the only element rather contained in S. We write the normalizer of X as, this would be the notation. We just write instead of the whole set S, we just pick the element in the set, the one element in the set. So we make some statements about this set. So let G be a group, and let S be a non-empty subset of G. then the normalizer of S is a subgroup of G. and if H is a subgroup of G, so take note of this. Up here, we are considering any subset, whether it's a subgroup or not. And we claim that the normalizer of a subset will be a subgroup of G. But now we have, if we restrict ourselves to subsets that are subgroups, then we can say some more. Furthermore, if H is a subgroup of G, then the normalizer of H is the largest subgroup in which H is normal. So H itself may not be normal in G, but you can create a subgroup in which H is normal, and that subgroup is called the normalizer of H. It can turn out that the normalizer of H is also equal to the whole of G. That is possible. But if it is not, then it will just be the largest subgroup in which H is normal. So the second thing you can say is that if K is a subgroup of the normalizer of H, then H will be a normal subgroup of KH. So if you pick any other subgroup of a normalizer, KH itself will be a subgroup, and H will be a normal subgroup of KH. So those are the statements we need to prove. So take note of that. There are three things we need to do. One is to check that the normalizer of a subset is a subgroup. And if the subset is a subgroup, then the normalizer is the largest subgroup in which H is normal. And any other subgroup, if K is any other subgroup of the normalizer of H, then H turns out to be a normal subgroup of this KH. So we also need to check that KH will be a subgroup if K is a subgroup of a normalizer. And so KH turns out to be a subgroup of G. We'll see why that happens. Are there any questions on this? So before you prove the theorem, it's usually important to understand what it's saying. That's the reason we have not moved to the proof. It's very important that you understand what the theorem says before you go to the proof. Otherwise, the proof will not be very useful. So there are those three things we shall prove. Let's first prove that the normalizer of S is a subgroup of D. So to prove that it's a subgroup, first of all, you confirm that it is not empty, because the identity element will always be in this set. I think that's easy for you to check. The identity element must be in this set. And that means we are dealing with a non-empty set. If you pick any two elements from the normalizer of S, we need to check if the product of the two elements will also be in the normalizer. So how do we check? We check if it satisfies the condition for it to be in the normalizer. So we just multiply xy by S. But since y is already in the normalizer, it means I can write ys as sy. And also, since x is also already in the normalizer, it means I can write xs as sx. Right? So I have xys is equal to sxy. And that condition means that xy, this product, is also in the normalizer because it commutes. Xys is the same as sxy. Any questions? So we have proved closure. The other thing we need to check is that it's closed with respect to inverses. So any element in the normalizer would also have its inverse in the normalizer. So if x is a normalizer, it means sx should be equal to xs. So we can multiply both sides of this equation by the inverse of x, and we end up with the next statement. So X inverse Sx will appear on the left-hand side. And on the right-hand side, now we'll have X inverse X, S. But X inverse X is just the identity. So that will be will leave us with just S. So essentially what we have shown is that X inverse Sx is equal to S. But this is precisely the definition of an element being in the normalizer of S. So this is, if you take X inverse as your element, then X is the inverse of X inverse. So this satisfies the condition for X to be an element of a normalizer. And therefore we conclude that, for X inverse rather. So this we can now conclude that X inverse is an element of a normalizer of S. So we have used both definitions. We remember when we defined the set, we have used both of them to prove. Any of them works. Anyone, we don't need both of them. Both they're equivalent. So you can pick any one of them to use, whichever is convenient. It'll be fine. So this proves that the normalizer of any subset will be a subgroup. We will look at. I've not done any concrete examples of this, but maybe next time we'll give some. What's important now is to understand that the normalizer of S is a subgroup of G. So the next thing is to check that the first part, the part that is numbered 1 in the theorem, is supposed to check that the normalizer of H is the largest subgroup in which H is normal. So now let's fix a subgroup of G. We call it H. So if you pick any element from H, then H inverse will always be equal to H because of closure, right? This is something you can prove. So all elements of H will behave like elements in the normalizer of H, and that means H will be a subset of a normalizer of H. So this means that H must be a subgroup of a normalizer of H. We know H is a subgroup already. Now we have confirmed that H will be a subset of the normalizer of H. And this means that H is a subgroup of the normalizer of H. Is that making sense? Solomon, you're not saying anything.
Yes. I'm flowing with you, sir.
Okay. Now for all X in the normalizer of H, so this is by definition. If you pick any element from the normalizer, then X inverse will always be equal to H, right? So if you think of H as a subgroup of a normalizer, this condition guarantees that H is a normal subgroup of a normalizer of H, right? So we have proved that it's a normal subgroup. So what is left is to show that you can't find a larger normal subgroup than the normalizer that contains H. So or rather, what I mean is you can't find another subgroup in which bigger than the normalizer in which H is normal. So let's pick any subgroup of G in which H is normal. So for us to prove our statement, we need to show that this subgroup cannot be bigger than the normalizer, or rather must be contained in the normalizer of H. So because H is a normal subgroup of K, if you pick any element, this small k from K, this statement will be true. We have assumed that H is a normal subgroup of K, so this statement must be true for any K you pick in this subgroup K. But now this condition is also what you need to satisfy to be in the normalizer of H. So if there's any other subgroup in which H is normal, then that subgroup, in this case we called it K, must be a subset of the normalizer. So it can't be bigger. It's a subset. It's contained in the normalizer of H. So we have proved that the normalizer of H is the largest subgroup of G in which H is normal. Any questions? Any comments? Okay, so muko mmeiva kabisa?
Tuko sawa.
Tuko sawa. Ama mnataka class iishe haraka ndio muulize maswali?
Hapana.
Yeah. Okay. Endelee. So and finally we proved 2. What was 2? Does anyone still remember what 2 was? We say that what? If K is a subgroup of a normalizer of H, then H is a normal subgroup of KH.
Of KH, yeah.
So let's assume K is a subgroup of a normalizer of H. Then for any elements you pick from this subgroup K, I've written this twice. I think need to delete one of them. We have the following situation. Since K comes from the normalizer of H, we have the situation KH, K inverse must always be equal to H, which means you can multiply by, post-multiply by K on both sides of this equation, and you will have KH is equal to HK. But then you can extend this further because this works for any value of K that you pick from this subgroup K, this will be true. This means that if the whole of KH must be equal to HK. Right? You can see. So now if this condition is true, then it means this product, HK or KH, since they're equal, it doesn't matter which one you pick, they must be subgroups. KH is a subgroup of a normalizer of H because we have picked 2 subgroups from this group, and the subgroups are K and H, and we have shown that KH must be equal to HK. And that condition we saw earlier when we were talking about subgroups, that if this is satisfied for 2 subgroups, then this product must be a subgroup. So we've established that KH is a subgroup. So we just need to establish that H is a normal subgroup of KH. I mean, you can tell that from this statement. This statement here tells you that H is a normal subgroup of KH. I think you can see why, because you have checked this for all elements in K. The only elements you have not checked are the ones in H, right? If you check for the ones in H, they should work because the elements in H do not change H. This will still be true. And now, but technically all these elements you pick were from the normalizer of H, so they can't be outside the normalizer of H, and therefore they must satisfy this condition for all values, or rather all elements in KH. So that means H is a normal subgroup of KH. So I think the proof is complete, unless there are any questions on that. No questions? So theorem, let H be an empty subset of G. Then H is a normal subgroup of G if and only if there exists a homomorphism from G to another group, G prime, whose kernel will be H. So what this theorem says is anytime you have a normal subgroup, it's possible to construct a homomorphism which with H as the kernel. It's always possible. So we'll go to the proof. We have, this is an if and only if statement. So we need to prove the theorem and its converse. So first we'll assume that if H is a normal subgroup, then it must be the kernel of some homomorphism from G to another group. So all we need to do is to find an example of such a homomorphism with H as a kernel, and that is what we do in the proof to show that it exists. So suppose H is a normal subgroup of G, then we know that this is a group, a factor group. The set of all left cosets of H in G is a group, and we can define this map from G to this factor group by psi of X is equal to XH. And this map is a homomorphism whose kernel is equal to H. That can be checked. I think we have proved this before, this map, right? So anyway, as an exercise, complete this. Show that this map is actually, this map as defined is a homomorphism. I think we proved earlier that it is a homomorphism. So conversely, suppose H is a kernel of some homomorphism from G to another group, G prime. Then automatically we also proved earlier that the kernel is always a normal subgroup. So that means H in this case will be a normal subgroup. And that proves the converse of the theorem. Any questions? So you have some work to do. You need to check that this map, which sends every element to the left coset determined by the element, you need to prove that that map is a homomorphism from the group to the factor group of G by the normal subgroup H. Any questions? Because Wally. So we move to the next theorem. This is a very important theorem. We call it the isomorphism theorem, but there are some books that will call it the first isomorphism theorem. I don't know if the name is that important. What is important is that you understand what it means or the implications of the theorem. We shall also look at the proof. So what does it say? It says if you have a map, a homomorphism from G to another group, G prime, then this factor group will be isomorphic to the image of the homomorphism. So the image is a subset of G prime, and we claim that this factor group, the set of all left cosets of the kernel of the homomorphism in G, will be isomorphic to the image of the homomorphism. So this is denoted by, now this is a typo. We need to have the forward slash here. The forward slash is missing. So this forward slash means a G, this set of this group, this factor group is isomorphic to the image. Are we together? We shall see it in the diagram. Was someone saying something? Thought I heard some sound. So technically, what this simply means is that you need to show that you can have an isomorphism from this factor group to the image of the homomorphism. Remember, the image is a subgroup of G prime. We showed that earlier. The image is always a subgroup of the codomain for a homomorphism. So basically, this will be a map from this group to this group, because the image is a subgroup, it's also a group. So you can define a map from this as a group to this one as a group, and you need to find one that is an isomorphism. And if you find one, then you will have proved that the two groups are isomorphic. And this is a shorthand. So this means that this group, the factor group G by the kernel, is isomorphic to the image. Is that okay? So let's prove this. So to make our work easier, we shall, so that we don't have to keep writing the kernel of this homomorphism, we shall make this substitution. K is equal to the kernel of phi. So we know that K is a normal subgroup of G, because the kernel is always a normal subgroup. So we define a map from the factor group G over K, G by K rather, to the image of the homomorphism. So the image of the homomorphism will be represented by this. So the map is defined as you pick a left coset and you map it. So this new map, not the symbols are different. So this is psi and this is phi. So psi will pick a left coset and map determined by x and send it to the image of x for all x in G. So at this point, we already know that this is a homomorphism. What we don't know is if this new map will be a homomorphism. So let's check. So to check that it's a homomorphism, we pick any two left cosets, find the image of a product of two left cosets, and K is a normal subgroup, so xk, yk is the same as xyk. So then I can get the image of xyk, and under the definition, this should be the image of xy under this map phi. And that means, since I already know that phi is a homomorphism, I can write this as phi x, phi y, but I know phi x is the image of xk, and phi y is the image of yk under this psi, this Greek letter psi, the map. So we confirm that this map is a homomorphism. So what's left is to check that it is surjective and injective as well. So to check if it is injective or one-to-one, if xk is equal to yk, this will be equivalent. Remember, we talked about the equivalence classes when we define an equivalence relation whose equivalence classes were the left coset, and we saw that if any two left cosets are equal, it means they're in the same equivalence class. This x and y must be in the same equivalence class, and they must satisfy this condition. X inverse y is an element of K. That means they're related under the equivalence relation that we defined earlier. So if X inverse y is in K, it means that now I should have written X inverse y here. If it's in the kernel, then it means it must be mapped onto the identity in the image, right? Which we shall call E prime. And then, but then this means that if that is the case, it means the image of X should be equal to the image of Y. I have skipped some steps in this simplification. You can fill that up yourselves. So the only change you need to make is that instead of X, Y inverse here, we should have X inverse Y. So using the properties of homomorphism, you can eventually show that this means that the image of X is equal to the image of Y. But if that is the case, also this means that the image of XK under this map psi will be equal to the image of YK under the map psi. So you notice that what we have here are the logical equivalents, the symbol. So these statements are logical equivalent so that the statement can also move backwards. Either way it works. So this guarantees that the map is injective. To show that it's injective, any element you pick in the image will be of this form. It will be the image of some element X in G. But then by the way the map is defined, this XK will simply be equal to pi X. So that means there's no element that is left out. Everything in the image has a pre-image from the factor group. You just pick the left coset determined by that element X and you have the pre-image. So that means the map is surjective, and therefore we can conclude that this we are defined a map from the factor group to the image, which turns out to be isomorphic. So it means the two groups, this image and this factor group, are isomorphic. So we conclude that this factor group by the kernel is isomorphic to the image of the map pi. So this is a very useful theorem, a very important theorem in algebra. If you choose to study algebra, you will encounter this a lot. It will be used in a number of places. So it's one very important theorem to master. Any questions? So one more statement we can make. If the map phi, if this phi is a surjective map, phi was a map from G to another group G prime, remember? So if it is surjective, then the image will be the whole of G prime. So this should be G prime, not G. It's a type. If you look at the map, just go back so that you get this, right? The domain is G prime and not G. So if the image is equal to the whole of G prime, then the kernel will be, this factor group will be isomorphic to the whole of G prime and not G. I seem to have, but if the image of phi is equal to G prime, so this should also be G prime. Then the factor group by the kernel is isomorphic to the whole of G prime. So these two should both be G prime and not G. Any questions? There are no questions. You can still hear me?
Yes.
Good. So here is a diagram that illustrates what you've just done. So we have this map from G, the group G, to G prime. The map is this phi. So we have another, this was not part of the theorem, but we can include it here. We have another intermediate map from G to this factor group of G by the kernel. And then the image of the map phi is what we have shaded in red. So this is the image of the map. So it's possible for this image to be the whole of G prime, but we shall consider the case where it is not. So our claim is that this factor group here, which consists of all left cosets of K in G, will be isomorphic to this red part, this image of this map phi. That's what the theorem says. So if you use this as our diagram, then we can factor this map into the image, this psi composed with phi. This phi is the canonical epimorphism. I think we defined that, the canonical which sends from a group to its factor group. It's a canonical map. The one I think we showed earlier that its kernel will just be K itself. The map from G to factor group by K, its kernel will just be K. Any questions?
No.
Okay. So here is another theorem that's also very important. It says that every subgroup, cyclic group rather, this off should not be there. So every cyclic group is isomorphic to either Z or Zn. So if it's an infinite cyclic group, it would be isomorphic to Z. If it's a finite cyclic group, it would be isomorphic to Zn for some positive integer n. So let's look at the proof. So suppose G is a cyclic group, then it means there must be some element in the group which generates the whole group, and we can call it A. So G will be the cyclic group generated by some element A. We can have more than one generator, but we just need one for this. So if A is a generator, then it means G can be written purely as powers of A, where M is some positive integer, not positive integer, M is just some integer. So we define a map from the group of integers Z to the group G by picking any integer and sending it to A raised to that integer. So, and remember, anything in G is just some power of A. So this is actually a map from Z to G. Clearly the map is surjective, because if I pick any element here, it will be of the form A raised to M. So I will just find a preimage in Z. That is always possible to find a preimage. So the map is definitely surjective. So what's the kernel of this map? Remember, the kernel would simply be the set of all integers which are mapped onto the identity in G. So if the order of the generator, or rather if it's a finite group, let's start with a finite group. If it's a finite group, then the order of the generator, and the order of the generator is S, then you will need, you will know that A raised to S will be equal to the identity, right? And any multiple, any integer multiple of S, when A is raised to that, you will still get the identity. Is that correct? So that means the elements that are in the kernel will simply be the multiples of S, where S is the order of the generator, A. So if order of A is S, then the kernel will simply be made up of the multiples of S. Now, if A is not of finite order, rather if G is an infinite cyclic group, then the kernel will just be only 0, right? And if the kernel is only 0, then it means this map is injective. So actually it's surjective, as we shall see, based on the isomorphism theorem. So if you apply the isomorphism theorem, if G is an infinite group, then it will just be isomorphic to, because the kernel will just be 0, it will be isomorphic to this factor group, which is just Z essence. The set of all left cosets of 0 in Z will turn out to be the whole of Z, or isomorphic to Z. Now, if G is a finite group and the number of elements in G are S, in other words, the same thing we said here, the order of A is S, that should give us a number of elements in G, because A is the generator of G. Then, since the kernel is simply the set of all multiples of Z, of S rather, so this being the kernel, it means that this factor group will be isomorphic to the image. Since the map is surjective, this factor group will be isomorphic to the whole of G. Remember the map, we have G is our codomain in this case. So the factor group will be isomorphic to G. So that's just an application of the isomorphism theorem. So we have checked in both cases, when the G is an infinite cyclic group, it will be isomorphic to this factor group, which is also isomorphic to Z, the group of integers Z. So it can be shown that this factor group is actually isomorphic to this group of integers modulo S. So this factor group will have exactly S distinct cosets of SZ, and also this one has exactly S elements, and there is an isomorphism between these two. So that eventually means that G will be isomorphic to ZS, where S is the order of the generator A of G. So again, this is a very important theorem. Any questions? So we want to apply these ideas we have learned and a few others we have done before to see how we can count homomorphism from one group to another. So we will focus on a simple case where both groups are cyclic groups, and we'll use this example where we find the number of homomorphisms from Z6 to Z8. So it's going to combine a lot of ideas that we have done before. Some may need to be proved, but I'll leave those for you as exercises. So you must remember most of what we have done before to answer this question correctly. So the first thing we need to do is determine all possible kernels And we know that the kernels are always normal subgroups. So we must pick all the possible normal subgroups of Z6. Because the map is from Z6 to Z8. The kernel will always will be a subgroup of Z6. Now we are lucky in this case because Z6 is an abelian group, and any subgroup of Z6 will be a normal subgroup. So if a subgroup of Z6 is a normal subgroup, then it's a candidate. We are not guaranteed that it will be a possible kernel, but it's a candidate. That it will finally be a kernel, but since all the subgroups are normal, we need to consider all of them. So the normal subgroups will be 0. This should be Z6, not Z. It should just be Z6. There's a subscript missing here. It should be Z6. Okay, so we have 0, the whole group itself, and then the subgroup K generated by 3, and also the subgroup H, which is generated by 2 or 4. And any of these, 2 is a generator, 4 is a generator. So we need to find the factor groups. So this one gives you the generators of the subgroups. K is generated by 3, the cyclic subgroup generated by 3. H is a cyclic subgroup generated by 2, but it can also be generated by 4. So any of these will be generators of H. And the whole group Z6 has 2 generators, 1 and 5. So this should be equals to, not comma. So 5 and 1 will generate all of Z6. We also need to know the generators of Z8. Z8 is generated by 1, 3, 5, or 7, the whole of Z8. We may not use that, but sometimes it's useful. So now with that information, let's assume that we have a homomorphism. Yes.
Kindly go back to the last. Okay, the slide it was before this one.
There's someone with the mic on. We're having a very serious conversation. But now it's off. You have a question on this part? Who has a question on this part? There's someone who asked me to come back here and they are now quiet. They're not saying anything. So can I move the next slide?
Yeah, you can move. I just want to put something down. Okay.
Okay, if you're done, then that's fine. So since we want to count the number of homomorphisms, we want to figure out if you have a homomorphism, how will it behave? So by the isomorphism theorem, we know that this factor group by the kernel will always be isomorphic to the image of the map, right? Earlier on, we also learned that the image must always be a subgroup of the codomain. In this case, the codomain is Z8, and the image is usually a subgroup of Z8. So Lagrange's theorem tells us that, or rather, before we go to Lagrange's theorem, we state that the image must have the same order as this factor group. If they are isomorphic, then the image cannot have more elements. It must have exactly the same number of elements as this factor group, since they are isomorphic. So the number of elements in the image must also be a divisor of 8 by Lagrange's theorem, because the image is a subgroup of the number of elements in Z8, and therefore, by Lagrange's theorem, for any subgroup of Z6 to be a kernel, the number of elements in this factor group for the index of the kernel must be a factor of 8, right? So since you already know the possible kernels, we can find their the index of each kernel will either be, or rather the number of distinct left cosets will be 1, 2, 3, and 6. So depending on which subgroup of Z6 you pick as a kernel. So if you pick the subgroup to be Z0, the subgroup with just the identity element, or rather if the kernel only contains 0, then the number of distinct left cosets will be 6, right? But now 6 is not a factor of 8, so 0 cannot be a kernel. If you pick the subgroup to be 03, the factor group will have 3 elements, or the index of that subgroup 03 will be 3, right? So that subgroup 03 cannot be a kernel because, just a minute. Yeah, because the index is 3, and 3 is not a factor of 8. So that cannot be a kernel. So we have the other subgroup, which consists of 0, 2, and 4. The index of that subgroup, which consists of only 0, 2, and 4, will be 2. But 2 is a factor of 8. So that subgroup 0, 2, and 4 can actually be a kernel. So the only possible images will be 0. If the only that is where the kernel is the whole of the whole factor group. Sorry, the kernel is if the kernel is the whole of Z6, right? Then the possible image will be 0. So that is the trivial homomorphism, where the kernel is the whole of Z6. Then the image will be this trivial subgroup. The other possible image will have index 2, right? The divisors of 8. 2 is a divisor of 8, so you need a subgroup of order 2. There's other divisors of 8 like 4, but none of these kernels will have index 4, right? So you can't have an image with 4 elements. There's also 8. None of these kernels can have index 8. So you can't have the whole of Z8 as a possible image. So the only possible images would be 0. And that 0 is if the whole of Z6 is a kernel. And the other one is 0, 4 as a possible image if the kernel is this group 0, 2, 4, K. So this should not be Z. This should be Z6. The kernel is Z6, and then the image is 0, because everything now will be mapped to 0, the identity in Z8. But if the kernel is 0, 2, 4, then this index of that kernel will be the number of elements in this factor group will be 2, right? Because the distinct left cosets of K will just be 2 of them. And that means the image must be a subgroup of Z8, which has 2 elements. And the subgroup of Z8 with 2 elements is this one, 0, 4. So for these different kernels, you can try to construct so the information is summarized here. So these are the subgroups of Z6. So the index of 0 is 6. So the 0 cannot be a possible kernel. It can't have any image because the homomorphism will not work. 0, 3 is of index 3. This should be 2. Should not be 2. This should be 3. Now 3 is not a divisor of 8. So this is not a possible kernel. And therefore you can't have any image as well. But 0, 2, 4 is of index 2. 2 is a divisor of 8. And therefore it's a possible kernel. And we have a subgroup of order 2 in Z8. Z6, the index of Z6 the whole group is just 1, and this it's a possible kernel because we have a subgroup with 1 element in Z8, which is a possible image. So this second homomorphism is easy to construct because every element in Z6 is just sent to 0. The one that may pose some challenges here is this one where the kernel is not the whole group Z6. So we shall see how to construct that. Now we observe that Z6 is generated by 1 and 5. Any of these two will generate 1 and 5. Now, a homomorphism will always map the generator of a cyclic group to the generators of the image. So you need to prove this. I've left that as some work for you. So we know that the generator of 0, 4 is equal to 4. So you can construct a homomorphism by simply starting with one of the generators in Z6 and mapping it to 4. So you could start from 1 to 4 and use that to compute all the other images, or you can send 5 to 4 and use that to compute all the images. So what we'll do is we will send 1 to 4 and use the assumption that this is a homomorphism. So if you send 1 to 4, we can find the image of 2 as the image of 1 plus 1. Remember, this is addition modulo 6. So I've just put 6 here to show that the addition here is in Z6. So 2 is the same as 1 plus 1. And since this map is a homomorphism, I can split this into 2 like that. But I know that now if on this end, my binary operation will be in Z8, because now at this point I'm operating in Z8. Right? But I've already sent my image. 1 has already been sent to 4. So I know that this will be 4 plus 4. But now my addition is modulo 8. And 4 plus 4 modulo 8 will be 0. So that means 2 will be sent to 0. Using the same ideas, we can confirm that 3 will be sent to 4. 4 will be sent to 0. And 5 will be sent to 4. 0, of course, will be sent to 0. You can do that by simply checking 0 is the same as 3 plus 3. And that means pi of 0 will be the same as 4 plus 4 in Z8, which is 0. So we have been able to construct the images of all the homomorphisms, of all the elements in Z6, using the fact that, using this fact here, that a generator will always be mapped onto the generator of the image. So this is only non-trivial homomorphism from Z6 to Z8. The other one was where the whole of Z6 is a kernel, so everything in Z6 is mapped onto 0. Are we together? Hey, do we one more?
Yes.
Okay. So that is true. Now this was a simple example. Sometimes the image may have more. Here we picked an example where the image has only one generator, which is 4. So if you have another example where the image has more than one generator, you can pick any of the generators at random and send one of the generators in the domain onto that generator and compute the images of all the remaining elements using these properties of homomorphisms. So here, just to be clear, this subscript here 6 means addition modulo 6. This subscript 8 here means addition modulo 8. You need to keep track of that. So you can see the construction here, where the kernel, if the kernel is this 0, 4, 0, 2, and 4. So that subgroup, if it's in the kernel, it means all its elements will be sent to the identity in Z8. and we have seen how that we obtained that. We started from 1 and were able to obtain all the images of the other elements. So this is the only homomorphism and trivial homomorphism from Z6 to Z8. The other homomorphism from Z6 to Z8 is one where Z6 is the whole of Z6 is a kernel. So everything in Z6 just goes to the identity in Z8. These are the only two homomorphisms you can get from Z6 to Z8. So it's possible to work on a more complicated example, but it was best to start with a simple one. Now, maybe in your own time, you can try to check what if you reverse from Z8 to Z6? How many homomorphisms can you have? There are similar questions in your tutorial. I can't remember which number it is, but there's a question which is similar to this, but with slightly bigger groups, cyclic groups. So you should attempt those questions with this information that you have. So any questions? So this brings us, the next one is a new topic. Can we have some questions? Next one is this new topic, we call it the symmetric group. I'm thinking maybe this is a good place to stop.
I have a question.
Ask.
Is that the? Oh, I was wondering whether that was the lattice group for Z6.
What do you mean by lattice?
Lattice groups.
Yes, we don't know them, so you need to tell us what are they, or where is the connection?
Lattice diagram is what I meant. Lattice diagram.
No, this is not a lattice diagram.
Oh, okay.
It is not. If I have not named it lattice, please don't name it. Don't set your own question. Just answer the question I have set. Nego? Yeah. Of course, you are free to read more on your own, but you have to, at some point, you have to focus on what is on the table first before you look elsewhere. Just master what is on the table. If you have mastered it, it's okay. You can go ahead and read more, but you're always better off if you move forward after you master what is on the table. So I think we agree that as much as you'd like us to continue, we have to stop. Am I right or am I right?
Right.
You are right.
So I will share the recording. I think I will stop the recording now. Let me make some corrections on these slides, then I share.